Good morning. My name is Vismit Joshi.
I'm David, or Qian.
I'm Max, too.
And our fourth year design project is on ZincOxide nanowires for ethanol gas sensing applications. In this seminar, what we'll first do is introduce the problem and its significance before presenting the current solutions available in the market. Then we'll present our improved design before moving on to the testing and validation phases, the key challenges, and the conclusion before wrapping up with the next steps and the acknowledgement. So ethanol is the active ingredient that's found in your favorite glass of wine. And sensing ethanol vapor particularly is critical for many different applications. This includes breathalyzers, which track your blood alcohol concentration. There's also food spoilage, where the bacteria will produce ethanol through fermentation, and when it goes above a certain level, you know the food is spoiled. And there's also industrial processes like oil sands and minings, where ethanol may be used and may be important to detect. And as trivial as it may seem, knowing ethanol levels will prevent illness and save lives. And that's the primary reason why we decided to pursue this project. Here are three main current solutions that are available. The electrochemical fuel cell is accurate and can be made very ethanol specific. However, it's expensive. We also have the infrared optical sensor, which is accurate, but it can be bulky, almost desktop sized, and it can also be expensive. And when it comes to the semiconductor-based sensor that we are pursuing, these sensors are cheap and portable, which also make them popular, but they have a moderate level of accuracy where there is room for improvement. This is also the type of sensor that is being used in current commercially available breathalyzers. Based on what we know about current solutions, what we did is we came up with some areas where there's room for improvement. These sensors can be made more portable, with higher accuracy, lower power consumption, and lower cost. Here's a general overview of our design that we are pursuing. For the semiconductor-based sensor, we are using zinc oxide nanowires, and what happens is the ethanol absorbs onto the nanowires and changes the resistance. And we see a very strong linear relationship between the resistance and the ethanol concentration. To give an overview of the mechanism, on the figure here we see the zinc oxide nanowire with the red electrons. What happens is when we expose it to air, oxygen will bind to this nanowire and becomes an anion, and the electrons will migrate towards the oxygen. This will give rise to a depletion layer, and that decreases the conductive cross-sectional area, which as a result increases the resistance. When we introduce a reductive gas like ethanol, it's going to attach to the oxygen molecules and it will leave, and that will as a result decrease the resistance. Based on this theory, we can use the concentration versus resistance calibration curve to detect ethanol concentration in real time. And this offers us some advantages like making a very light and portable sensor that has low power consumption and is reasonably accurate. To grow these nanowires, we used the hydrothermal method, and we grew these on a 3-inch glass wafer. What we first did is we deposited a zinc oxide seed layer by slow sputtering. And what this does is it acts as a nucleation center for the growth of these nanowires during the process. After that, what we do is we heat zinc nitrate with HMTA in a 1-to-1 ratio at 85 degrees Celsius for 1 hour. And during that process, the glass wafer is immersed in the solution with the seed layer, and the nanowires grow. What we do after the wafer has been dried is we sputter deposited aluminum electrodes through a shadow mask. And how do these components come together to integrate into a system? So our prototype here shows the most active component, which is the sensor. And this sensor is the nanowires that are between these electrodes that we see on the figure on the bottom left. Since these voltages and currents between the two electrodes tend to be very small, we had to amplify this to measurable values. What we then do is we measure the resistance between those two electrodes with the Arduino Uno printed circuit board. And what it does is it measures the voltage, and we convert this voltage to a resistance based on the circuit schematic. Then we use this standard curve to convert this to parts per million concentration of ethanol, and we display the results real time on a PC. The flow chart here shows us how the signal travels in the system, from the sensor to the amplifier, to the Arduino that makes the measurements, and finally to the PC that displays the outputs.
So there are three major testing phases. The first one will be right after the fabrication process. We want to see if we got the optimal nanowire mesh to make sure they have a solid contact. And then if we got our optimal mesh, then we'll move on to the probe testing to see if we could get a really solid signal. And then we will move on to do the actual ethanol vapor concentration test by putting into a text box with controlled parameters. And the first one, so SEM concentration. So if you can see those three batches of sensor sample we have grown, and the first two actually are failed ones, and we actually overgrown them. They are actually in this vertical kind of orientation that there's like too little space in between, and you can see the micron-sized wires are actually nucleated on top of it, which you can tell like this would not give a good like contact into the metal contact we printed on after, and so we have to bring down the temperature we grow our nanowires in to actually get the third one, where you see it's in the size of 100 nanometer size, and it's actually having like good mesh of like this kind of contact to the metal contacts. And to do all of these, obtain these characterization images, we have to use the only one in QNC that can give us these images. Other ones cannot give us like to about 60,000 times of magnification to bring those clear images. And the last image is where we figure out our optimal nanowire growth procedure that was mentioned before in an 85-degree with 1 hour of growth time. And then we move on to our probe testing stage. So we just want to see if we could get and we do get our ohmic behavior for our sample. Basically, we could use it as a variable resistance for the ethanol gas testing. And we also tested with different varying channel distance. So like the one with the highest slope is with 1 millimeter distance, and the one almost plateaued is the one from the top to the end, to the bottom. So this is what we expected, because when you increase the distance, you will have a larger resistance value. And with this signal, and also if you see the order on the y-axis, this is why we decided we have to use an amplifier circuit, because it's in the -7 order. And also it's a good indication that it is a lower power consumed device. And then we move on to our ethanol vapor concentration test. So the procedure is starting by, we measure the text box we use, and for each spray, how much of the ethanol gas can be put into the environment. Then we put the sensor in at the bottom of the text box, and then we spray a certain amount of ethanol each time into the box, and we wait till it entirely evaporated, and then we got the data from Arduino for the voltage recording, and then we just repeat this stage with different concentration and different input of ethanol, and then get a higher concentration. And then we would got this strong linear relationship between the resistance and the concentration in ppm. And so however, so from the various test results we have got is like, it will always get a linear relation, but the difficult part is to bring all the baseline to this, having the same baseline because of the environmental changes, such as, so even we do a purge session after, but even if that, we're still not gonna, like every time having the ethanol or like impurity is completely cleaned out for next session. And also if we put in different temperature or pressure or humidity, because it will have different kind of effect on the, so this is what we're gonna overcome if we're gonna put this into an improved solution. So for the key challenges of this project, the first one is on the fabrication process. So we had like several stages growing nanowire samples to get to the optimal solution, and to actually go use the SEM to figure out that's the best one. And then throughout the testing, we figure out then we need some circuit and sensor protection. So maybe adding some layer of protection, then we could help like not hurting the circuit and sensor, and also help purging the gas molecules for the next testing. And we will also need to think about, so for compensation for the environmental changes, maybe we next need to add in some more components, such as some oscillators to, like, when temperature changes, then we can compensate for that change to have the same or close starting resistance baseline value. And the last will be the scaling of this whole project, because growing nanowires in the mesh, but if you grow the next batch, even in this controlled area, the mesh would not be the exact same orientation or composure. And so it would not be in the same kind of results you use from the previous batch. So you need to kind of have some kind of tuning kind of strategy to make them, or like produce a different kind of formula for this batch, and to produce also accurate results. And this will be the last key challenge. And
okay, so just to summarize what we have done so far, first we determined our optimal nanowire mesh growth procedure, and we did this by characterizing the nanowires that we have grown using SEM. After that, we tested our device for its electrical resistance values, and because the resistance was too low, we decided to incorporate an amplifying circuit into our design to make the signal more detectable, as well as incorporating our Arduino Uno to get real-time measurements that are observable on our laptops. Our tests also reveal that our circuit design works well, and that our sensor behaves in a linear manner with respect to different ethanol concentrations. In terms of next steps, the testing procedure and setup can be improved upon. First of all, our current method of attaching our wires onto our device is quite a simple and basic method. We ran into some issues where the wires would just come off because the electrical tape that we used was not strong enough. One way to fix this is to use silver paste instead of the conductive wires, and to firmly attach the wires onto the contacts. Another area where we can improve upon our testing procedure is to separate the evaporation phase of our ethanol and the sensing phase. And this will allow us to basically get a more accurate response time, because right now the response time takes a few minutes, but most of that is because we are waiting for the ethanol to evaporate in our test box. So if we theoretically had a setup where we could just let ethanol vapor flow in and then purge it afterwards, it would make testing the response time much more accurate. Another thing that we can account for is to calibrate our device based on and take into account temperature, humidity, and pressure, and determine coefficients for those three variables. Another next step that we can do is make our device a standalone, handheld, and battery operated, so that it's easily portable and we can transfer it and use it outside or wherever we want. And finally, we can after the above points that I mentioned are done, we can move on to different gases such as hydrocarbons like methane, propane, as well as other gases such as ethanol. Thank you for listening to our presentation. Do you have any questions?